As we jump into our Module 10, we're going to be taking a look at convection, including energy transfer by both the bulk fluid motion, known as advection, and the random motion of fluid molecules, known as conduction or diffusion. So within this, we're going to provide an understanding for the physical mechanisms that underlie convection transfer and develop the means to perform convection transfer calculations. We're also going to take a look at the physical origins and discuss those, along with the relevant dimensionless parameters and some important analogies that are going to be developed. So objectives within this Module 10, we're going to take a look at the convection boundary layer, discuss the local and average convection coefficient, look at laminar and turbulent flow, talk about the boundary layer equations, get into the boundary layer similarity. We're going to be discussing the normalized boundary layer equations, talk about the physical interpretation of the dimensionless parameters, as well as getting into some discussion with the boundary layer analogies. So relating this to our textbook, this is Chapter 6. We're breaking this into two different sections. We're going to go with Module 10.1, which is going to be Chapter 6, Sections 6.1 to 6.4, and then we'll get into Module 10.2, which will be Chapter 6, Sections 6.5 through 6.8. So for our first section, Module 10.1, we're going to begin our Chapter 6 talking about an introduction to convection, looking at flow and thermal considerations. So within this module here, we're going to take a look at the convection boundary layer, both the fluid and thermal boundary layers, talk about local and average convection coefficient for heat and mass transfer. Then we'll get into some laminar and turbulent flow, looking at velocity boundary layers and thermal and species concentration. And then last, we're going to get into the boundary layer equation for laminar and compressible flow. So activities within this module here, we'll go through the governing theories for the above discussed topics here, look at our governing and key equations, talk about some practical applications, and then go through some problem solving together. So then this module, we'll be taking a look at Chapter 6, the Introduction to Convection, looking at our flow and thermal considerations. This relates to Chapter 6 and Sections 6.1 through 6.4. We'll also be taking a look at Appendix E, specifically E1 through E3. So as we begin this module, I want to take a look at boundary layers. In particular, let's take a look at the physical features. Now, if we're going to introduce this concept of a boundary layer, what we want to do is we want to consider the flow over a plate. And we can see that in this diagram here. We have a flat plate right here with flow over it. Now, when the fluid particles make contact with this surface, the velocity is then going to be reduced significantly relative to the fluid velocity upstream of the plate. So now I want to take a look at our velocity boundary layer. Now with this here, the boundary layer velocity profile is going to refer to the manner in which our U term right here varies with our Y. So you can see our Y coming up off our flat plate right there through our boundary layer. Now with this, the fluid flow is going to be characterized by two distinct regions. The first one being our boundary layer, or a thin fluid layer, in which our velocity gradients and shear stresses are large. And then also we're going to consider a region outside of the boundary layer. And in this here is where our velocity gradients and our shear stress are going to be negligible. So now as we get a further distance away from our leading edge, we're going to see that the effects of the viscosity penetrate farther into the free stream and the boundary layer grows. So what we can say is that our delta right here is going to increase with x, and we can see this in the shape of that velocity profile right there. And this is our term, delta with respect to x. So to summarize our velocity boundary layer, this is a consequence of the viscous effects associated with the relative motion between a fluid and its surface. So that's what we have over here in our diagram. We see our surface and we have a fluid above it. So a region of the flow is going to be characterized by shear stresses and velocity gradients. And we'll get into some governing equations for our shear stresses associated with this. Now, as we mentioned, this is going to be a region between the surface and the free stream. So we have our surface right here, and now we can see right here, we have this free stream right there, whose thickness, there's our thickness right here, our delta, and again, this is going to increase with the direction of flow. So we can see the direction of our flow right here is going in our positive x direction. So we can see that from the arrows denoted there, so that's the direction of our flow. We can see our delta is increasing in the direction of our flow right there. So with this increasing distance, farther from this leading edge out right here, so there's our leading edge right there, the effects of our viscosity penetrate farther into that free stream, and the boundary layer again is going to grow. So again, our delta is going to increase with our x. Now our velocity boundary layer is going to be manifested by a surface shear stress, or tau sub s. Now this is also going to provide a drag force, or F sub d. So this surface shear stress, or tau sub s, is given by equation 6.2 in our textbook. So we have this relationship here, and we can see our F sub d is right here. So for our surface shear stress, if we're assuming a Newtonian fluid, the surface shear stress may be evaluated from the knowledge of the velocity gradient of the surface. And that's what this equation right here, 6.2, is, where this mu right here is a fluid property known as our dynamic viscosity. Now in the velocity boundary layer, the velocity gradient at the surface depends upon that distance x from the leading edge of the plate. Therefore, our surface shear stress and our friction coefficient will also depend on this value for x. So now that we've discussed the velocity boundary layer, let's take a look at our thermal boundary layer next. So this thermal boundary layer is going to be a consequence of the heat transfer between the surface and the fluid right there. So there again, there's our surface and our fluid, and now it's a consequence of the heat transfer between those two. So this is going to be a region of flow that's going to be characterized by temperature gradients and heat fluxes. Now, this is also a region between the surface and the free stream. So there's our free stream right up there again. There's our surface right there, whose thickness are delta sub T now, because T sub T right here is for thermal. This is our thermal boundary layer right there. This is going to still increase with our flow direction. So again, our flow is moving in a positive x direction. So we can see our delta sub T here being dependent upon x and increasing by this shape right here from our leading edge. So now the question is, why does delta T increase in our flow direction right here? Well, what we can think about here is with our increasing distance from that leading edge, the effects of our heat transfer are going to penetrate further into that free stream, and the boundary layer effects are going to grow. So our thermal boundary layer is going to grow as we go further along in our x direction. So a thermal boundary layer is going to be manifested by a surface heat flux. So this is right here, equation 6.3 right here. There's our surface heat flux right there. Our Q double prime sub S, where S, our indice indicates our surface right there. And also a convection heat transfer coefficient, H right here, where H is given to us in our equation 6.5 in our textbook by this relationship that we see here. So now let's ask yourself this question here. If our surface temperature and our surrounding temperature, Ts minus T infinity, are constant, so if this Ts minus T infinity is constant, then how does our Q sub S here double prime, or our surface heat flux, and our H value, our convection heat transfer coefficient, vary in the flow direction if this temperature difference right here is constant? Well, the way we can think about this is, since that temperature difference right here is constant, that means it's going to be independent of our direction x. So while our delta T increases with increasing x, our temperature gradients at the boundary layer must decrease with an increasing x. So therefore, accordingly, the magnitude is going to decrease with an increasing x, and therefore it'll show us that our Q sub S double prime, or our surface heat flux right here from equation 6.3, and our H values are going to decrease with our increasing x as well. So now I want to talk about the difference between a local and average heat transfer coefficients. So let's first take a look at our local heat flux and coefficient. So this relates back to our equation 6.4 in our textbook on page 380. So we can see this relationship here. We have our surface heat flux, our Qs double prime, is equal to our H times our temperature difference of Ts minus T infinity, where Ts is our surface temperature that we can see right there. There's our T sub S, and T sub infinity is our surrounding temperature up here for the diagram on the right. So now let's take a look at average heat flux and coefficient rather than our local for a uniform surface temperature. So this is going to relate to equations 611 through 613 on page 382 and 383 of our textbook. So let's take a look at our first equation here for our heat transfer rate. Q is equal to our H bar times our A sub S times our temperature difference of T sub S minus T sub infinity right here. We see T sub S is our surface temperature. There's our A sub S right on that surface as well. And there's our surrounding temperature, T sub infinity. And again, this relates back to our equation 6.12 on page 383 of our textbook. Now that's just this one point right here. What if we want to do this for our total heat rate? So our total heat rate Q can be obtained by integrating the local flux right here all over the entire surface. So if we integrate our local heat flux right here, we can do this with our relationship shown in equation 6.11 on page 382 of our textbook. So we have our relationship here that our total heat transfer rate here, Q, is equal to the integral over A sub S times our heat flux right here from this equation up above there times dAs, which is then equal to, pull out our constant right here, this is our temperature difference right here from this relationship up top there once we plug in, Ts minus T infinity. So our surface temperature minus our surrounding temperature times the integral over As of our H, there's our H again from that top equation up there for local, times dAs. So again, this relates back to our equation 6.11 on page 382 of our textbook to get that total heat transfer rate, Q. So this brings us down now to our equation 6.13. What we can see here is that the average and local convection coefficients are related by this expression. So we can see our H bar right here for our average local convection coefficient is equal to our 1 over AS times the integral of AS times H dAs. So that's how we relate our average H value with our H value right there. And you can see this is that average H that we're plugging into this equation 6.12. Now, in particular, for a flat plate and parallel flow, like we see in our example over here, we can see that our H bar right there, or our average local convection coefficient, is equal to 1 over L. In this case here, we can see L is that length right there, times the integral from 0 to L of H dx as we're going in our x direction right there. And this relates now to equation 6.14 on page 383 of our textbook. And this is for our average and local convection coefficients right there. So you can see that average and our local right there, H bar and our H. So let's get into the math a little bit here and take a look at the derivation of some of these equations. So if we start out with our equation 6.10 from page 382 of our textbook, we have right here that our heat transfer rate Q is equal to the integral over AS of our heat flux times dAs right there, where from equation 6.4 we had this relationship here that our heat flux is equal to our H times our temperature difference of Ts minus T infinity. So what we can do is we can take this relationship here and plug it back in to our equation 6.10. So if we plug in 6.4 to 6.10, we end up with this relationship down here that our Q is equal to the integral over AS of our, now when we plug in for right here, our Q prime, this is now our H right there, times Ts minus T infinity, times now dAs right there. So the next thing that we can do, this is an integral here, we can pull out our constants. So we already said that these are going to be constants right here. So we can pull these out in front of our integral. And now we can see that Q is equal to that temperature difference of Ts minus T infinity times the integral over As of H dAs. And this is our equation 6.11 that we see on page 282 of our textbook. So just a little derivation, going through some math here on how we can go between these different equations and how they were derived. So now I want to take a look at our boundary layer transition. We'll refer to this diagram we see here. We can see we have our laminar region, our transition, our turbulent region right here. We have our streamline. We also have our x going over positive this way, and we have our y positive up like this here. So what I want to do is let's ask ourselves a few questions and try to characterize this boundary layer transition. So how would we characterize the conditions in the laminar region of the boundary layer development? So now we're here, we're just looking at our laminar region right here from our diagram. So what we can say about this here is that the fluid flow is going to be highly ordered, and we can see that right there. It's very highly ordered, and it is possible to identify streamlines along which the fluid particles are going to move. So that's what we can say about our laminar region. So next we'll discuss our turbulent region right here. So now we're going from this point to this point here in our turbulent region. So in the turbulent region, how do we characterize the conditions of our boundary layer development? Well, the flow is going to be highly irregular and is characterized by random 3D motion of relatively large parcels of fluid, and we can see that shown in our diagram right here for our turbulent region. So now we've discussed our laminar region and our turbulent region. Now what about this region in between, our transition region right here? So what conditions are associated with that transition from our laminar to our turbulent flow? Well, the conditions within the transition zone right there, so we can see that transition zone right here, change with time, with flow, sometimes exhibiting laminar behavior and sometimes exhibiting the characteristics of turbulent flow as well. So we can see that there. You can see sometimes we have here what we've characterized before is our laminar flow, and then we're starting to get into some of this right here that looks a little bit closer to what we've determined as our turbulent flow. So now I want to continue on with our discussion of Reynolds number. So why is the Reynolds number going to be an appropriate parameter for us to use in order to quantify this transition from our laminar to our turbulent flow? Well, the onset of turbulence is going to depend on whether the triggering mechanisms are either amplified or attenuated in the direction of our fluid flow. So this is the direction of our fluid flow right here. Now, are these going to either be increased and amplified, or they're going to decrease and be attenuated, which in turn is going to depend on the dimensionless grouping of parameters, which is then referred to as our Reynolds number. So this is why we're going to use our Reynolds number there for quantifying this transition from our laminar to our turbulent flow. So for our example here, we have a flat plate and parallel flow. We have the transition criterion given by our critical Reynolds number relationship here. So we have that our critical Reynolds number is equal to our density times our u sub infinity. We can come back up here and take a look. There's our u sub infinity right there, our velocity right there, times our x sub c. We can see our x sub c is this distance right here up to the transition region. So that's our whole laminar region right there represented by x sub c, all divided by mu. So this is our relationship utilizing our critical Reynolds number for our transition criterion. For our specific example, we're looking at a flat plate and parallel flow. Now, just a side note here, this x sub c, again, if we go right up here to this x sub c, it goes up to this point right here. This is our x sub c right here. And this is the location at which the transition begins to turbulence right there. So this is our relationship as we look at this for our problem here. So for a critical Reynolds number for a flat plate and parallel flow, we have that this right here would be greater than 10 to the 5th, but it's going to be less than 3 times 10 to the 6th for this critical Reynolds number. So let's take a look at our relationship between our Reynolds number and our transition. So what can be said about transition? If our Reynolds number is going to be less than our critical, we're going to be laminar in that case there. And what can we say if our Reynolds number is greater than our critical Reynolds number? Then in that case, we're going to be our turbulent. So now let's take a look at the effect of transition on the boundary layer thickness, our delta, and our local convection coefficient, our H value right here. So we have this graph shown down here in our figure below. So we can see down here on our x-axis, we have our x sub c, which again corresponds to that laminar region right there. Then we'll have our transition region, and then we're going to have our turbulent region after that. So what happens to our H value, our local convection coefficient in this laminar region? Well, we can see right here for our H right here, H of x right here, as our x increases in this laminar region right here, we can see our H value decreasing by this graph right here in this curve. Now this is kind of opposite to what we see occurring for our thickness right here, our delta right there. We can see during our laminar region, this is going to be increasing with our x up till the end of our laminar region until we hit transition. You can see there's a steep change right here once we hit that transition region. So once we hit that transition region, going back to our H value here, our local convection coefficient, we can see a huge spike as we go through that transition region all the way up there as we increase in our x direction there. Then we hit at the end of our transition region for our H value, we can see then when we hit our turbulent region after the transition region, it's going to slowly decrease back down in our x direction. Whereas if we're taking a look now at our boundary layer thickness right here, our delta value in our transition region, we can see right there, it does increase substantially right there, a little spike in our increase in our thickness right in our transition region, goes up to the end, and it mellows out but still increases as we get into our turbulent region right there for our delta x and our direction of motion right here, our x direction. So what can we say about this with our relation to our transition region? Well, what we can say is that our transition provides a significant increase in the boundary layer thickness right there. And we can see that right there. There's our significantly increase right there in our boundary layer thickness during our transition region right there. So the turbulent mixing produces large temperature and species concentration gradients adjacent to the solid surface, as well as the corresponding increase in our heat and mass transfer coefficients across that transition region from there to there. So as we saw in the figure above in that graph there, we can see that the convection coefficient, our H value, is going to decay during our laminar region. So we see that right there. There's a decay during our laminar region there. And it increases significantly with no transitions to turbulence, despite the increase in our boundary layer thickness right there. So you can see that's what we talked about here, that steep slope right there in our transition region. And then the convection coefficient decays in the turbulent region, as we discussed before when we look at this right here, as we get into that turbulent region there. So these are our effects of transition on our boundary layer thickness, our delta, and our local convection coefficient, H. So moving on, I want to now take a look at our boundary layer equation. So we can improve our understanding of the physical effects that determine the boundary layer behavior and then further illustrate its relevance to convection transport by considering equations that are going to govern the boundary layer conditions. And now we can see that these are going to be illustrated over here in this figure on the left. So now within this figure we have here, we can see we have our delta T, our thermal boundary layer, and we also have our velocity layer right here, thickness right there, our delta. We can see this is our positive X going off this way, our positive Y going up here. We have our surrounding temperature and velocity there. We can take a look at an element that has dimensions of dy, dx. Here's our heat flux from the surface right there. And we can then see our T sub infinity and our U sub infinity right there. And right down here now we can see our tau sub s right there, and then we could see our surface temperature T sub s right here. So all this is going to be included within this diagram for us to reference back to as we're looking at these equations for our boundary layer. So what we want to do is we want to consider the concurrent velocity and thermal. So again, there's our velocity and thermal boundary layers right there, delta sub T, and our delta right there for the thickness of the thermal boundary layer and our velocity boundary layer respectively right there. So we're going to consider though the concurrent velocity and thermal boundary layer development for a steady state, two-dimensional, incompressible flow with constant fluid properties. So those are a lot of assumptions right there that we're making to simplify this down. Steady state, two-dimensional, incompressible flow, and has constant properties. Constant properties that we're talking about here is our mu, C sub p, and our K value right there. And also we're going to consider that it's going to be negligible body forces. So again, a lot of simplifications and assumptions within this problem here for coming up with these boundary layer equations. So what we want to do to derive these boundary layer equations is we're going to apply our conservation of mass, Newton's second law of motion, and our conservation of energy to a differential control volume, so there's our differential control volume up there, and invoke our boundary layer approximations. So as we take a look at our velocity boundary layer equations, we can relate this back to the equations 6.25 and 6.26 in our textbook. So if we take a look over here at this equation here, what we can say here, if we take a look at the partials within this, the gradients normal to the object surface are much larger than those along the surface. So as a result of this, we can neglect the terms that represent the x direction diffusion of momentum, thermal energy, and our chemical species relative to their y direction counterparts right there. So that's what we're saying for this relationship here. Now on our right side over here for this equation, now what we can say is that because the boundary layer is so thin at this point right here, that the x direction pressure gradient within the boundary layer can be approximated as free stream pressure gradient. So that's some little notes that we can do if we're talking about our velocity boundary layer equations related to 6.25 and 6.26 in our textbook. So now let's take a look at our thermal boundary layer equation. So this right here relates to equation 6.25 in our textbook. So we have these partial differentials right here. We say our delta squared T over delta X squared is much less than our delta squared T over delta Y squared right there. So again, in our X direction is going to be much less than in our Y direction. So moving on from there, we can now take a look at our conservation of mass, and this relates to our equation here of 6.27 in our textbook. So we have our delta U over delta X plus delta V over delta Y right there. So our partial of U with respect to X and our partial of V with respect to X, when we add those two together, this is going to be equal to 0 according to this equation 6.27. So the thing to note that our U and V are going to be our mass average fluid velocity components with units of meters per second. So note here, this equation is an outgrowth of applying the conservation of mass to the differential control volume element that we saw on the previous slide in that figure there, which has a volume of dx times dy times 1. Now these two terms in the equation represent the net outflow, or the outflow minus inflow of mass in the x and y directions, the sum of which must be 0 for steady flow. So that's why the right-hand side of our equation, we add these two together, is 0. So now let's take a look at the application of Newton's second law of motion. So with this here, let's just take a look at our x direction, and we'll relate this back to our equation 6.28 in our textbook. We'll break this down into 3 different parts right here. Let's first take a look at the left-hand side, which I have boxed in green. This is the net rate at which the x momentum leaves the control volume due to its fluid motion across the boundaries. So we have u times our partial of u with respect to x plus v times our partial of u with respect to y for this here. Then moving on to the right-hand side of our equation right here, the first term is going to be our net pressure force. So we have this as our negative 1 over our mass density times the change in our pressure in our x direction. So dp infinity over dx. And this is going to be plus now. We deal with our third term within this equation right here in red. And this is the net force due to our viscous shear stresses right there. So we have our V times now our delta squared U over delta Y squared. So this equation is going to be a result of the application of Newton's second law of motion that we talked about right there in the x direction for that same differential control volume, our dx dy times 1 right there in the fluid that we saw on our previous figure on the previous slide. So now let's take a look at our conservation of energy. So our conservation of energy is going to relate to our equation 6.29 in our textbook, and we're going to break this equation down into 3 parts as well. Let's take a look first at our left-hand side of this equation here. Box this in green. We have u times our partial of t with respect to x plus v times our partial of t with respect to y. And what this is the net rate at which the thermal energy leaves the control volume due to our bulk fluid motion right here, or advection. Now dealing with the right-hand side of our equation, let's take a look at the first term that I boxed in yellow here. Now this says our alpha times our delta squared t over delta y squared. This is going to be the net inflow of the thermal energy due to y direction conduction. And last, we'll deal with our final term over here in red, and this is what remains of the viscous dissipation right there. So we have V over C sub P times our du over dy partial of u with respect to y squared. So this all combines to our equation of 6.29 in our textbook. So let's ask yourself this question. What is the second term on the right-hand side of the equation called, and under what conditions may this be neglected? So this is our second term on the right-hand side of our equation. What do we call this? Well, this is our viscous dissipation right there. And when can this be neglected? Well, there are many situations this term can be neglected relative to those that account for advection and conduction. However, aerodynamic heating that accompanies the high speed, especially supersonic flight, is a noteworthy situation where this term is going to be important and we don't want to neglect it. So now let's go ahead and apply some of that theory and governing equations that we saw within this module to an example problem. So let's take a look at example problem 6.3. In this problem here, they tell us that in a particular application involving airflow over a heated surface, that the boundary layer temperature distribution can be approximated by the following relationship that they give here. Now within this governing equation that they give us right here, y is the distance normal to the surface, and we give our number here, our PR number right here, is equal to this relationship right here, which they give us a value of 0.7. Now this is a dimensionless fluid property. Now if they also tell us that our T sub infinity is equal to 400 K and our surface temperature T sub S is equal to 300 K, and we have our ratio here as 5,000 meters to the negative 1, what they want us to find now, our surface heat flux. So a thing to note before we get into solving this problem, we can get some of these thermophysical properties from our table A4 based upon the temperature that they give us for this. So this is thermophysical property of gases at atmospheric pressure right here. So we can go down here for air to a temperature of 300 that they gave us right here, and we can find our K value right here. So we can utilize this table A4 as we go through the solution to this problem. Now let's take a look at problem 6.3. In problem 6.3, what we have here is we have a particular application involving airflow over a heated surface. The boundary layer temperature distribution is approximated by the following. So we have here T minus Ts over T infinity minus Ts is equal to 1 minus the exponent of negative PR times U sub infinity Y over our V value there. Now down here we define what some of these are, where Y is going to be the distance normal to the surface, and the Prandtl number PR is equal to C sub P, or specific heat, times mu over K, which they give us a value for this of 0.7. So we can plug that directly in up above there. This is a dimensionless fluid property. We also know that T sub infinity is given to us as 400 K, and T sub S is given to us as 300 K. And we have this ratio here for U infinity over V equal to 5,000 meters to the negative 1. So what they want us to solve for in this problem is what is the surface heat flux. So surface heat flux is what we're going to be looking for. So now that we've had a chance to look through the problem statement, what we want to do next is go through and figure out what they give us, what we're looking for, or are there any assumptions we need to make. So if we go back to the word problem, they give us quite a bit of information. One thing that they give us here is our T sub infinity, which is our air temperature, and this was given to us as 400 K. They also give us this ratio of U infinity over V is equal to 5,000 meters to the negative 1. We have our T sub S, or our surface temperature, is equal to 300 K. We have our PR number is equal to 0.7, which is also equal to this relationship here, C sub P mu over K, where this is a dimensionless fluid property. So we have a numeric value for this as well. We also have, given in the problem statement, our governing equation here, which is our boundary layer temperature distribution relationship. So this is T minus T sub S all over T infinity minus Ts, where T sub infinity, as we recall from above, is our air temperature. T sub S is our surface temperature, and this is equal to 1 minus E to the negative PR U sub infinity over V, there's that ratio again, times our Y value there. So now we have this governing equation here. What I do next is I draw out a little diagram. And what we can see in this diagram, here we have over here our ambient properties here for air. So there's my T sub infinity, there's my U infinity over V, there's my PR number right there, all for the air over here. Then I have my surface right here. Here's my T sub S, so the surface temperature. And then right here, I have my equation of T minus T sub S over T infinity minus T sub S that we see above here for our boundary layer temperature distribution. So we can see how this visually is illustrated here in our diagram. Now, the question is, what are they asking us to solve for? So in the problem, they asked us to solve for the surface heat flux, or variable terms are Q sub S double dash. So now that we know everything that we're given and what we're looking for, we need to figure out our first step in our solution. So the first thing that we're going to want to do when we start solving this problem is to go to table A4 and get the properties for air at 300 K. Because we saw above here in our given information, we have our temperature of air right there, and we have our temperature at the surface right there. So we need to use this information in order to go back to table A4 and get our K value. So now let's switch back to table A4 and take a look. So now we open our textbook to Appendix A8 on page 995, and we look at A4. Thermal physical properties of gases at atmospheric pressure. So we go down to our temperature. Temperature is given to us as 300 K. Now we go across here. We're looking for our K value here. So temperature 300 K. Go over here. We have 26.3 for value. But we want to pay attention to here is our units here. So it's watts per meters times Kelvin, which is perfect. But this is K times 10 to the third. So let's pay attention to that when we plug this in back in our normal equation. So now that we've had a chance to go to table A4, back of our textbook, we can look at the properties for air at 300 K. K is equal to, when we take into account that 10 to the third from the table there, 0.0263 watts per meters times Kelvin. Now we can take a look at an approach for our solution. We start with is our governing equation. This governing equation can be found on page 380 of our text for equation 6.3. In equation 6.3, we have our heat flux, or Q double prime S, is equal to a negative Kf of the partial dt over dy evaluated at y is equal to 0. So now that we have this relationship here, the next step is to go ahead and rearrange the given expression for the boundary layer temperature distribution. So that's the equation that we were given in the problem statement there, shown down below here. So we want to rearrange this guy here, and the first thing that we want to do in this rearrangement is to solve for our temperature difference here, our T minus Ts. Ts is our surface temperature again. So in order to do that, we can multiply our numerator or denominator here, T infinity minus Ts, over onto the other side. So we end up with this expression here, that T minus Ts is equal to 1 minus e to the negative PR
u infinity y over v, all times now t infinity minus ts that we took from the denominator here and multiplied over. So now we have this relationship here, and what we can see that our t minus our ts is a temperature difference here, or a change in temperature delta t. So call this partial delta t here, so that is equal to, again, that same expression on the right there now. So now that we have this, the next step that we want to do is to take the derivative of this function with respect to dy. So before we move to the next step of our solution, we need to review some calculus. So if we go back to our calculus, we can see that if we take the partial of some function e to the ax with respect to x, we get a solution in the general form of a e to the ax, where a is the constant in the exponent here of e to the ax, so that comes down in front. Now we get a e to the ax is our general form. So now we want to apply this calculus to our particular equation. So d over dy of our function, our expression here, looks like this. Now what we want to do within ours is figure out what are our constants. Well, we know 1, that's a constant there. I'm going to pay attention to our sign convention throughout this whole thing still. And then over here we have PR as a constant, and u sub infinity over v is a constant as well. And we have this t sub infinity minus ts that are both constants. So now we have these constants here. They can come out as our a term when we do our partial here. So we now have, once we carry down our negatives, negative t sub infinity minus ts times negative PR times the ratio here, u sub infinity over v, times e to the negative PR times u sub infinity delta y over v. So now we have our solution in this general form from calculus here, from our equation here when we took the partial with respect to y. So the next thing we want to do with an expression like this is to try to reduce and simplify. So the first thing that we notice is we have some negatives here that can cancel out. So we can cancel out those negatives, and what we end up with is our partial of our t function here with respect to y is equal to, once the negatives go away, t sub infinity minus t sub s times PR times u sub infinity over v times e to the negative PR times u sub infinity delta y over v. So now that we have this in a form here for dt over dy with partial, we can plug this back into our heat flux equation. So if we do that, our heat flux equation, q sub s double dash, is equal to our negative k times t infinity minus ts times our PR times u sub infinity over v, all times e to the negative PR u sub infinity delta y over v, evaluated when y is equal to 0. And if we recall where this comes back from equation 6.3 on page 380 of our text, when we defined this as our heat flux for a surface right here, or this general expression here. So this is our dt dy. So that's why we're plugging this right here back in right there for this equation, and we end up with what we see here for our heat flux. So now that we've plugged into that equation for our heat flux, what we want to do is pay attention to the right-hand side of that, where it told us to evaluate it when y is equal to 0. So that's exactly what we're going to do. We're going to go through here, plug in our y of 0. So right here was our delta y. Plug this in as 0. So this whole term now becomes 0 if that's 0 there. So e to the 0 then becomes 1. So this whole right side of the equation now comes to 1 here. So now we have that our heat flux is equal to negative k times our temperature difference between t sub infinity minus ts times our PR number times this ratio here of u sub infinity over v. So now we have a lot of known values that we can reference back to page 1 of our solution to look at. So we can plug in all of these values here. So again, our k was our lookup from the table. Our t sub infinity and ts were given in the problem statement. Our PR was given in the problem statement. And this ratio here, u sub infinity over v, was given in the problem statement as well. Pay attention, put our units in so we can do unit analysis to make sure everything checks out. So now we have our q sub s double dash, our heat flux here, is equal to a negative 0.0263 watts per meters times Kelvin times 400 Kelvin minus 300 Kelvin times 0.7 times 5,000 meters to the negative 1. So we look here, well, these two combine to a Kelvin there. There's a Kelvin there. Those will cancel out. So we do the math, plug this in. We end up with our heat flux is equal to a negative 9,205 watts per meter squared when we do our unit analysis. Our units check out. And this negative implies convection heat transfer to the surface.
So now let's take a look at my hand solution going through another example problem. In this case, let's go through example problem 6.7. In this problem here, they tell us that we have a parallel flow of atmospheric air over a flat plate of length given to us of L is equal to 3. Now this is disrupted by an array of stationary rods placed in the flow path over the table. So we can see this in our diagram below. Now, laboratory measurements of the local convection coefficients at the surface of the plate are made for a prescribed value of V and T sub s greater than T sub infinity. The results are correlated by an expression that they give by the formula here for h of x, where h of x has these units here and x is in meters. They ask us to then evaluate the average convection coefficient right here, our h bar L, for the entire plate, and that ratio as well at the trailing edge.
Let's take a look at problem 6.7. So in this problem here, we have parallel flow of atmospheric air over a flat plate with a known length of L is equal to 3 meters. This is disrupted by an array of stationary rods placed in the flow path over the plate. So we can see here, here's our stationary rods. There we have our atmospheric air flowing over the flat plate down here. We can see the plate starts over here, moves in the x direction to a distance L. We have our T sub s for the surface temperature, our T sub infinity for the surrounding ambient temperature of the air over here. And now what we also know is the laboratory measurements of local convection coefficient in the surface of the plate are made for a prescribed value of V, and T sub s is greater than our T sub infinity. So our T sub s is greater than our T sub infinity. The results are correlated by an expression of the form h sub x is equal to 0.7 plus 13.6x minus 3.4x squared, where our h sub x has units of watts per meter squared times Kelvin, as we'd expect, and x is in meters. They want us to then evaluate the average convection coefficient, our h value, for the entire plate and our ratio here at the trailing edge. Now that we've had a chance to read through the problem statement, what we want to do next is to organize this in a nice, neat format, similar to what we've done the homeworks and exam problems before, where we have a list of everything that's given to us in the problem statement, variable names, units, values, redraw and simplify our diagram, and write out explicitly what they're asking us to solve for. So we take a look at this, and we can see in the problem statement for problem 6.7, they give us that the total length is equal to L, from there to there, which is equal to 3 meters. They also give us an expression for our h of x. So this is given by this equation here of 0.7 plus 13.6x minus 3.4x squared in units in watts per meter squared. So now that we've had a chance to take a look at problem 6.7 problem statement, the next thing we want to do is go through everything that they tell us in that and organize it in a manner that we can quickly reference back to. So do that by using our format that we've used in all of our homework and exam problems. We write out everything that's given to us in the problem statement, variable names, values, units, and then we redraw a simplified version of the given diagram or schematic. And then at the end, we look explicitly at what they're asking us to solve for. So for our particular problem here, for parallel flow over a flat plate, we read back through the problem statement, and we can see that they give us the total length L, the flat plate, as 3 meters. We have our expression for h of x in terms of this relationship equation here, 0.7 plus 13.6x minus 3.4x squared, with units of watts per meter squared. We know it's a flat plate. We know that there's parallel flow. We know that there's stationary rods that the air is flowing over. We have also the variables v, T sub s, and T sub infinity, where we know that the surface temperature T sub s is greater than that of the surrounding air temperature T sub infinity. Now they're asking us to solve for two different things here. The first thing they're asking us to solve for is the average convection coefficient for the entire plate, which this is our h bar over L. They're also asking us to solve in part B for the ratio of our h bar over L, or the average convection coefficient, over our HL at the trailing edge. So the next step is to start going through our solution, and where we want to start for this is looking for our governing equation. So based off of what they told us in the problem statement, we know that it's a flat plate in parallel flow. So based on that information, we can go to page 383 of our textbook to take a look at equation 6.4. So this will give us our governing equation for the beginning part of our solution here for this problem. So we have h bar, our average, is equal to 1 over the length L evaluated from 0 to the total length L of h dx. So this is our governing equation we're going to use here. So the next step in this is to go through and start plugging in what we know, what our known values are. So we're given an expression, an equation for our h of x value here. So that's where we're going to replace this from our governing equation here at 6.14 with that value from our problem statement here. So that's the first step here. Now h bar is equal to 1 over L evaluated from 0 to L. Plug in this equation here of 0.7 plus 3.6x minus 3.4x squared dx. So now that we have this plugged in here, the next step is to break this down and do out our calculus. So what we can do is I take the integral of each individual component of this here. So I break this apart. H bar is equal to 1 over L times now the integral from 0 to L of the first part of this, 0.7 dx, plus the integral of the second part of this, 0 to L of 13.6x dx, plus the integral of the third part over here, integral from 0 to L of minus 3.4x squared dx. So when we do out our calculus for each of those three parts there, the integral of 0.7 dx is equal to 0.7x evaluated with limits of integration 0 to L. Then we take the integral of 13.6x relative to dx becomes 1/2 x squared times our 13.6, and we pull our constant out front, evaluated from 0 to L. And then we take the integral of this last part over here, and again, this is from still the limits of integration of 0 to L here, of 3.4x squared dx. So we do this out here, and this becomes 1/3 x cubed times our constant we pull out front of 3.4, evaluated from 0 to L. So now that we've gone through and performed the integrals on our h of x function here for each individual part, the next thing I want to do is go through with our limits here, plug those in from 0 to L for each of those, and take a look and see what we can reduce and simplify and what cancels. So when we plug this in from 0 to L, we end up with 0.7 L. Plug in for our limits from 0 to L here, we end up with 6.8 L squared. And over here, when we plug in from 0 to L, we end up with 1.13 L cubed. So now I take a look, and out front here, we have a 1 over L. So that cancels with this L here and eliminates it. That cancels with the squared here and leaves us with just an L. And that cancels with the cubed here and leaves us with an L squared. So then we reduce this down. We end up with our average H is equal to 0.7 plus 6.8 L minus 1.13 L squared. Now what we do know here is we have a value for L. The total length of the plate of L is equal to 3 meters. So we can take this L is equal to 3 meters and plug it back in for our values for L here. So when we do that here, our average H is equal to 0.7 plus 6.8 times that 3 meters minus 1.13 times 3 meters squared. So we plug those in, end up with average H is equal to 0.7 plus 20.4 minus 10.17, or our average H is equal to 10.9 in units of watts per meter squared times Kelvin. So now that we've solved for the first part of our solution here, where we've evaluated the average convection coefficient for the entire plate, the next thing we want to do is go back to that original problem statement and see what else we need to solve for. When we do that, we go back and realize that they also asked us to solve for the ratio of our average convection coefficient over our H of L value at the trailing edge. So now we're going to need to come up with a method to determine our H of L. So what we can do here is realize that our H of L is simply our H of X expression, the equation that they give us in the problem statement, evaluated at X equals 3. And this is because the total length, our L, is equal to 3. So what we can do is take this expression right here for h of x and plug in x equals 3 for this in order to get a value for h of L. So we do that here. We say x is equal to 3. Plug that into our h of x expression here. So we end up with h of L is equal to 0.7 times this 13.6 times 3 meters minus 3.4 times 3 meters squared. We can go through 3 squared is 9, do out the math here. And we end up with a value now of h of L is equal to 10.9 with units of watts per meter squared times Kelvin. So now that we have that, we have an h of L and we have an h of L bar that we solved for previously, we can now do the ratio that is asked us to solve for. So when we do that out, we realize our h of L bar is actually the same value as h sub L that we've just solved for here. So if we go back to the previous page of our solution, we can take a look. Well, when L was equal to 3 meters here, we went through and plugged into this expression after our calculus, we still ended up with a value of h bar is equal to 10.9 watts per meter squared times Kelvin. So once we plug that value in to our ratio here, we get 10.9 over 10.9, which gives us a value of 1. Now the thing to note is this is unique for this value of x equals 3, and there's an existence of a maximum for h of x at some x here that occurs when x equals 2 meters that we could go back through and solve for that maximum. So again, this is unique only to x is equal to 3 meters for the solution for this ratio equal to 1.